When a test pilot takes a completely new, not yet fully understood type of combat aircraft into the air for the first time, he rarely does it alone. Flying nearby, often at very close, visually controlled distances, is another aircraft, known as a chaseplane, performing a number of critical safety functions for such a test flight. The main task of the escort aircraft pilot is constant visual observation of the test aircraft from the outside, from a point of view that is physically inaccessible to the test pilot himself, who is inside his own cockpit. This may seem obvious, but such external observation can reveal critical problems that are completely invisible from inside the aircraft itself, for example, signs of fuel or hydraulic leakage, visible only from the outside of a plume of smoke, or unusual behavior of individual external structural elements, deformation or partial destruction of some external element, which went completely unnoticed by onboard sensors, but is clearly visible to the experienced eye of an escort pilot observing the aircraft from the side in real time. The pilot of the escort aircraft, as a rule, is himself an extremely experienced test pilot, often having previously tested similar types of aircraft, and is able to instantly recognize the slightest deviation from the normal, expected behavior of the test aircraft in flight, which the test pilot, completely focused on executing a specific test program and flying his own, as yet insufficiently studied aircraft, may not have time to notice in a timely manner himself. In addition to purely visual observation, the escort aircraft is often equipped with additional specialized photographic and video equipment capable of capturing detailed images of the aircraft under test in various flight modes, with high resolution and special angles inaccessible to conventional ground-based imaging equipment, which is subsequently extremely valuable for engineering analysis of the real behavior of the new design in the air, and not just based on data from onboard sensors. In the event of a serious emergency during a test flight, the escort pilot is also able to provide critical voice support to the test pilot, helping him to assess the external situation in real time, coordinate a safe return to the airfield, or, as a last resort, decide whether to eject based on an objective external picture of what is happening, which is not available to the pilot located directly inside the potentially damaged or malfunctioning aircraft. The tradition of using escort aircraft when testing new aircraft goes back to the very first decades of test aviation and remains an integral, mandatory part of the flight testing process of any fundamentally new military aircraft to this day. Despite the enormous progress in the field of onboard diagnostic systems and telemetry, which transmits data on the condition of the aircraft under test to ground specialists in real time, the human eye of an experienced pilot observing the behavior of a machine directly next to it in the air still remains an indispensable element in ensuring the safety of the most risky, very first flights of new aircraft. A small bird weighing only a few hundred grams can, in a high-speed collision, cause damage to a combat aircraft comparable in severity to being hit by a small artillery shell. This is not an exaggeration. The laws of physics are ruthless here. The kinetic energy of an object grows in proportion to the square of the speed, and the relatively small mass of a bird at the speed of a fighter turns into a destructive projectile. The military departments are paying enormous attention to this seemingly insignificant threat at first glance, having developed an entire specialized program called BASH, Bird Aircraft Strike Hazard, a program to reduce the threat of aircraft collisions with birds. The first area of struggle is managing the environment directly around the airbase. Wildlife management specialists at military airfields work deliberately to make the area surrounding the airfield as unattractive as possible for bird gatherings. This includes vegetation management. Certain types of grass cover are significantly less attractive to foraging birds than others, elimination of water and food sources that attract birds, and, where possible, some impact on nearby landfills and other sources that traditionally attract large concentrations of birds that may be dangerously close to takeoff and landing areas. The second direction is the active scaring of birds immediately before and during flight operations. This may include the use of special sound devices that reproduce the cries of birds of prey or alarm calls of specific species of birds native to the area, the use of laser scaring devices, and in some cases, trained birds of prey, falcons, or hawks, specially kept at some military and civilian airfields specifically for regular patrol and scaring away smaller birds from the adjacent area of the runway. The third direction is the collection and analysis of data on seasonal and daily migration routes and bird activity in a specific basing region. Specialized radar systems, initially based largely on technologies similar to conventional weather radars, are capable of tracking the movement of large flocks of birds at a significant distance from the airfield, allowing controllers to temporarily adjust takeoff and landing routes or, in some cases, briefly suspend flight operations until a particularly dense concentration of birds passes through the airfield area. The fourth, less obvious direction is the design of aircraft engines itself has already been mentioned earlier in the context of bird ingestion tests, but it is important to understand that such stability of the engine design is the last line of defense, applied precisely when all previous preventive measures have not worked and a bird strike still occurs in flight. Despite all these multi-layered measures, it is impossible to completely eliminate the risk of bird strikes. It remains one of the few natural threats against which even the most advanced military technology is forced to rely primarily on preventive rather than purely technological protective solutions. The U-2 reconnaissance aircraft flies at an altitude of more than 21,000 meters, almost twice the cruising altitude of a conventional passenger airliner. At this altitude, the atmospheric pressure is so low that human blood would literally boil at body temperature if not for special protection. That is why the U-2 pilot wears not an ordinary flight suit, but a full-fledged high-altitude spacesuit, almost indistinguishable from an astronaut's suit. Why are a regular oxygen mask and a pressurized cabin not enough here? At altitudes above 19,000 meters there is a physiological boundary known as the Armstrong line. Above this limit, atmospheric pressure is so low that liquid water, including fluids in the human body, boils at normal body temperature without the need for additional heating. This condition is called ebulism, and without proper protection it can lead to death literally within seconds if depressurized. The U-2 cabin is, of course, sealed and maintains excess pressure. But the history of operation of such high-altitude aircraft knows cases of sudden depressurization of the cabin due to a technical malfunction or combat damage, and it is precisely this critical case that the pilot's spacesuit is designed for. A full high-altitude suit consists of several layers. The inner layer provides ventilation and thermoregulation, since the temperature outside at such an altitude can drop significantly below -50 degrees Celsius. The main sealed layer is able, if necessary, to independently maintain pressure around the pilot's body, even if the pressure in the aircraft cabin completely drops to the values of open space at a given altitude. A spacesuit helmet is a separate, complex engineering device that provides oxygen at a certain pressure directly into the pilot's respiratory tract, regardless of the ambient pressure inside or outside the cabin. Putting on such a suit before a flight is a long, carefully regulated procedure that can take more than an hour, with the participation of specially trained personnel checking the tightness of each connection and the correct fit of each element of the suit individually for a particular pilot. U-2 pilots, before long high-altitude flights, also undergo a mandatory pre-breathing procedure with pure oxygen for about an hour before departure. This allows dissolved nitrogen to be washed out of the blood and body tissues, reducing the risk of developing decompression sickness, similar to what threatens divers when quickly ascending from great depths, since a sharp transition to conditions of extremely low atmospheric pressure at high altitude creates a similar physiological risk. The uniqueness of the U-2 mission, long, many-hour reconnaissance flights at extreme altitudes in conditions that are most uncomfortable for the human body, requires such serious physiological protection for the pilot that in terms of complexity and purpose it comes close to a real spacesuit, although formally this aircraft never leaves the confines of the Earth's atmosphere. The runway is one of the most vulnerable, yet critical parts of military aviation infrastructure. Even relatively minor damage to a runway caused by a bomb or missile can completely paralyze the combat operations of an entire airbase if the airfield does not have a sufficient length of undamaged area for the safe takeoff and landing of combat aircraft. How do military engineering units solve the problem of quickly restoring the strip during combat operations? There is a specialized military discipline known as Rapid Runway Repair, RRR, worked out to the smallest detail in numerous exercises precisely because in a real conflict, the cost of restoring the combat capability of an airbase after an attack is literally hours, and sometimes tens of minutes. The first stage after the strike is a quick assessment of the damage. A specially trained engineering reconnaissance team, often using rapid visual inspection and, more recently, the use of unmanned aerial vehicles to minimize risk to personnel, determines the exact number, size and location of impact craters on the runway, and also assesses the presence of unexploded delayed action ordnance, which the enemy often deliberately uses precisely to hamper and slow down the process of restoring the strip. The second stage is demoning and neutralizing detected unexploded ordnance, which is a separate, extremely dangerous task that requires special qualifications, often preceding direct repair work. The third stage is the actual physical restoration of the damaged area. Here, a proven technique using fast-hardening repair materials is used. The impact crater is first cleaned and leveled using special engineering equipment, filled with layer-by-layer compacted aggregate, and then a special coating is laid on top. These can be quick-setting concrete mixtures, specially designed to achieve sufficient strength within a matter of hours instead of the usual several weeks for building concrete, or, which is used much more often in field conditions precisely because of the speed, prefabricated mats made of high-strength lightweight materials, laid directly over a temporarily backfilled crater, capable of immediately supporting heavy military aircraft loads immediately after installation, without the need for a long curing period. The key tactical concept of rapid repair is not the ideal, major restoration of the entire damaged surface of the strip, but the fastest possible creation of a minimum sufficient, safe for operations section of the strip of the required length and width, often offset from the original center line of the strip in order to bypass the most seriously damaged sections of it, the temporary repair of which would require much more time. The standards developed in regular exercises allow an experienced, well-equipped engineering team to ensure the minimum combat capability of the runway required for takeoff and landing operations within a few hours after the strike, a time that would be completely unthinkable using conventional, capital methods of road construction, but which is achieved precisely thanks to specialized materials and equipment developed and prepared in advance exclusively for such wartime scenarios. When a pilot ejects over hostile territory, or a sailor is stranded overboard in the open ocean, or a person needs to be rescued in conditions inaccessible to normal rescue services, one of the most elite and specialized branches of the U.S. Air Force comes to the rescue, the Pararescue Jumpers, known for short as PJs. Their motto, "so that others may live," accurately reflects the very essence of this specialty. Unlike conventional combat rescue helicopter crews, PJs are full-fledged special-purpose paramedics, capable of not only removing a victim from a dangerous zone, but also providing full-fledged emergency medical care of the highest level directly on the spot, in the most extreme conditions, including an active combat situation. Pararescue candidate training is considered one of the longest and most physically grueling training programs in the entire United States military, often taking 2 years or more, with exceptionally high attrition rates at each individual stage. The program includes intensive physical training comparable in its demands to that of elite special forces units, full-fledged diving training for conducting rescue operations on and underwater, including work in the equipment of an autonomous diver, advanced parachute training, including the technique of a high-altitude skydive with a delayed parachute opening, allowing for covert landing from a great height at a minimum distance from the landing point, as well as extensive medical training. Volume and complexity approaching the training of an advanced-level civilian paramedic, and in some aspects even exceeding it, taking into account the specifics of providing assistance in conditions of active combat operations. The tasks performed by the Parachute Rescue Service are extremely diverse. This includes the previously mentioned rescue of downed pilots in enemy territory, the rescue of sailors and passengers from shipwrecks on the open ocean, the evacuation of wounded military personnel directly from the battlefield in conditions inaccessible to conventional medical evacuation teams, and participation in civil disaster rescue operations, which require unique skills in landing and assisting in difficult terrain. It is PJs who often parachute directly or descend from a hovering helicopter directly into a combat area, where conventional rescue equipment cannot safely approach, in order to stabilize the condition of a wounded or downed pilot before the main evacuation forces arrive. This service remains relatively little known to the general public compared to the more publicized Special Forces units, but it is on the shoulders of these specialists that the direct responsibility for saving many lives of military personnel lies in the most critical and seemingly hopeless situations over many decades of military conflicts. Listening to recordings of real conversations between military pilots in the air, an uninitiated person will hear a stream of short, abrupt phrases, often completely incomprehensible without special training. This is not a random feature of speech under stress, but a strictly standardized system known as the brevity code, designed specifically to convey critical information as quickly, unambiguously, and reliably as possible under conditions of extremely limited time and high levels of background noise and stress. Why is such a specialized system needed instead of ordinary, colloquial speech? In a critical air combat situation, a pilot may have literally a split second to inform a friend of an immediate threat, coordinate a joint maneuver, or confirm the execution of a critical command. An ordinary, detailed conversational phrase would take much more time to pronounce and, what is important, to be clearly understood by the interlocutor in conditions of strong background noise, communication interference, and natural distortion of the voice under the influence of stress and physical overload. Standardized short terms solve this problem. For example, a short word denoting an immediate missile threat, spoken in a specific, pre-agreed and practiced way, instantly, without the slightest ambiguity, communicates to all group members the need for immediate protective action, without requiring additional clarification or detailed explanations at a time when every second is critical. Beyond the sheer speed of information transfer, clarity of understanding is critical. Standardized terms eliminate the possibility of misinterpretation of what is said, which is especially critical in joint operations involving pilots from different units or even different allied countries, where ordinary, informal spoken language might contain regional differences in pronunciation or meaning of words that increase the risk of misunderstanding at a critical moment. There are separate, highly standardized categories of code terms for various aspects of an air operation, terms to indicate the type and direction of a detected threat, terms to coordinate the joint maneuver of several aircraft, terms to confirm the execution or impossibility of executing a received command, terms to report the status of one's own weapons and fuel. A separate important category is call signs, used instead of the real names or tail numbers of pilots and units in radio communications, which serves both the purpose of reducing the length of the transmitted message and the purpose of certain operational security, making it difficult for an enemy potentially intercepting radio communications to accurately identify specific units or individual pilots. Mastering this specialized communication system is an obligatory and very extensive part of the training of any military pilot, since in a real combat situation the ability to instantly and unambiguously convey or perceive critical information through a standardized code of brevity often turns out to be no less important for survival than the direct skills of piloting or using onboard weapons of an aircraft. Behind the strict, official, highly technological exterior of military aviation lies a rich, informal cultural tradition that originated during the First World War and has survived to this day almost unchanged: squadron emblems, personal call signs of pilots and a whole set of unwritten traditions that play a much more important role in maintaining the morale and cohesion of the flight personnel than it might seem at first glance. A squadron emblem, or patch, is a unique identifying mark of a particular aviation unit, often containing an image of an animal, mythological creature, or symbol reflecting the history, nature of the mission performed or the combat reputation of a given squadron, sometimes accumulated over decades, and in some cases over more than a century of continuous existence of a particular unit. Many such emblems have a rich history, dating back to the formation of the unit during one of the World Wars, and are deliberately preserved almost unchanged for decades by subsequent generations of pilots precisely as a symbol of continuity and connection with the combat history and traditions of the unit, even despite the fact that the types of aircraft the squadron flies could change many times during this time. The pilot's personal call sign is a separate, rich cultural tradition. In contrast to the strictly functional, standardized tactical call signs used directly in radio communications during combat operations discussed earlier, there is another category of call sign, an informal, often ironic or humorous nickname assigned to a pilot by his fellow soldiers, usually shortly after arrival in a new unit, and remaining with him, in some cases, throughout his flying career. The assignment of such an informal call sign often occurs as part of a certain humorous ritual, and the call sign itself is often associated with some funny, awkward, or memorable incident that happened to the pilot early in his service in this particular unit, or is an ironic play on words based on the pilot's last name, or reflects some noticeable personality trait, sometimes presented in a humorously exaggerated or even deliberately contrary to reality form. Such a tradition performs an important social and psychological function within the tightly knit team of a combat squadron, where pilots regularly trust each other with their own lives in real combat conditions. An informal call sign contributes to the formation of closer, less formal interpersonal connections within the unit, reduces the psychological distance between pilots of different ranks and experience, and generally helps to strengthen that special combat camaraderie, which many military aviation veterans call one of the most important factors determining the effectiveness and coherence of a unit's actions in a real combat encounter. This informal cultural tradition, which originated more than a century ago, continues to exist almost unchanged in the most modern, technologically advanced air forces of the world, clearly demonstrating that even in the most high-tech environment, the human, cultural element of the military collective remains an integral and truly significant part of combat effectiveness. The physical and psychological condition of each military pilot is constantly monitored by a specialist in a special medical specialty, an aviation doctor, flight surgeon, whose role is much broader than the usual idea of a military general practitioner. Aviation medicine is a highly specialized field of medicine that studies the specific effects of flight on the human body, ranging from the already mentioned physiological effects of overload and hypoxia, to less obvious but no less important aspects such as the disruption of circadian rhythms during long flights across multiple time zones, the psychological effects of prolonged exposure to a confined cabin space during hours-long combat missions, or the cumulative, long-term impact of regular overloads on the spine and cardiovascular system of a pilot over a long-term flying career. The most important, in many ways unique feature of the work of an aviation doctor is that, unlike most other military doctors, he himself is obliged to regularly fly with the flight crew he serves, personally experiencing all the same physical stress as the pilots he supervises. This allows the aviation doctor to have a much deeper and practical, rather than purely theoretical, understanding of the actual conditions in which his patients work, which is critical for an accurate and adequate assessment of their physical and psychological condition. One of the most delicate and at the same time most important aspects of the work of an aviation doctor is the constant, delicate balance between caring for the health of a particular pilot and ensuring the overall combat effectiveness of the unit. A military pilot who informs a doctor about any physical ailment or psychological stress, even if insignificant at first glance, objectively risks being temporarily or even permanently suspended from flying, which for many professional military pilots represents a serious personal and career blow. This sometimes creates a subtle but very real temptation for pilots to hide certain symptoms from medical personnel, which, in turn, requires the aviation doctor to have special professional tact, the ability to build genuine trust with the flight personnel served, and at the same time, the ability to identify potentially hidden problems that pose a real threat to flight safety. Aviation doctors also play a key role in investigating the causes of flight accidents, which will be discussed separately below, by assessing whether any physiological or psychological factor in the pilot's condition played a role in the accident or emergency. In addition, it is aviation doctors who develop and constantly improve detailed medical protocols and recommendations for specific types of aircraft and their specific physiological loads, starting from the already mentioned anti-G suits and high-altitude spacesuits, and ending with recommendations for sleep, nutrition, and recovery of pilots between long combat missions. This highly specialized, but extremely important medical discipline remains a largely invisible part of military aviation to the general public, but it provides that critical element of the human factor, the health and performance of the pilot, without which the most advanced military equipment simply cannot be effectively used in a real combat situation. In the context of a large-scale military operation, the airspace over a specific combat area can simultaneously contain dozens, and in some large operations, hundreds of different aircraft, fighters, attack aircraft, bombers, tankers, reconnaissance and transport aircraft, drones and helicopters, each of which performs its own mission, often at different altitudes and with different priorities. How is the safe, conflict-free coexistence of such dense air traffic ensured, especially given the fact that in a combat situation there is no familiar civilian air traffic control system? This task is solved through a complex system known as airspace deconfliction, a pre-planned, detailed structured distribution of all available airspace over a combat zone into many separate, clearly demarcated zones and altitude levels assigned to specific types of missions or specific units for a certain period of time. This distribution occurs at the stage of detailed planning of an air operation, long before the actual start of flight operations, and is formalized in the form of a detailed document known as the Order of Air Operations, Air Tasking Order, which is distributed among all participating units and contains comprehensive information about which forces, at what time, at what altitude and in what specific geographic sector of the airspace should be, thereby minimizing the very possibility of accidental intersection of the routes of different aircraft performing fundamentally different tasks. In addition to the static, pre-planned distribution, the previously mentioned AWACS system plays a critical role in providing dynamic, real-time tracking of the position of all friendly aircraft in controlled airspace and early warning of dangerous proximity or potential route conflicts that were not or could not be fully anticipated during the initial planning stage. Additionally, strict procedural restrictions are applied, for example, a clear separation of high-altitude echelons between fighters patrolling airspace at high altitudes and attack aircraft operating much lower directly against ground targets, as well as specially designated, strictly limited in time and place, flight corridors for refueling aircraft and transport aircraft, minimally intersecting with zones of active combat operations of fighter and attack aircraft. A separate challenge is the integration into the overall deconfliction system of the number of various unmanned aerial vehicles that has significantly increased in recent decades, many of which operate at altitudes similar to manned aircraft, but are controlled differently and require their own, specific coordination protocols with the rest of the air traffic in the operation area. Even with all the care of such planning, the actual combat situation often introduces unforeseen adjustments, the need for emergency maneuvering in the face of a sudden threat, a change in route due to unexpectedly detected meteorological hazards, and urgent reorientation of forces to a new, higher priority target, and it is the ability of the airspace deconfliction system to flexibly adapt to such unplanned changes in real time, while avoiding a dangerous collision of friendly aircraft, is considered one of the most important indicators of the overall level of organization and effectiveness of a large-scale air operation. After any serious flight incident involving a military aircraft, be it a crash with the death of the crew or a relatively less serious incident without loss of life, a detailed, extremely thorough investigation begins, in which a key role is played by the onboard flight data recorder, informally known as a black box, although in reality this device, contrary to popular belief, is most often painted in a bright orange color precisely to facilitate its detection at the scene of the accident. Military aircraft are typically equipped with two separate types of such recorders, each with its own function. The flight data recorder records a huge number of different technical parameters of the aircraft: speed, altitude, position in space, readings of almost all onboard systems, position of controls, and many other technical parameters recorded with high frequency throughout the flight. The second type, the cockpit recorder, records voice communications between crew members and, where applicable, communications between the crew and controllers in other aircraft, providing investigators with critical information about what exactly happened in the cockpit immediately before the accident, what decisions the crew made, and based on what information was available to them at the time. Both types of recorders are structurally designed to survive even the most serious flight accident as reliably as possible. They are enclosed in an extremely durable, fire-resistant housing that can withstand enormous mechanical overloads upon impact with the ground, exposure to an open flame for a certain time, and, for aircraft capable of flying over water, significant pressure at great depths in the event of a fall into the ocean. The investigation of a serious flight accident in military aviation is usually carried out by a special investigative commission, independent of the immediate command of the affected unit, including experienced pilots of the aircraft type, aviation engineers, the previously mentioned aviation doctors, as well as specialists in specific onboard systems potentially related to the incident. The investigation is usually much broader than a simple analysis of flight recorder data. It includes a detailed physical examination of the aircraft wreckage at the accident site, if available for examination, a full analysis of the technical maintenance history of the particular aircraft, including all previous repairs and identified technical malfunctions, a detailed study of the training preceding the incident and the current physical and psychological condition of the crew, as well as an analysis of meteorological conditions and the general tactical situation at the time of the incident. The final conclusions of such an investigation are not always made widely public, especially if the incident is related to secret technical systems or a classified military operation, but the identified technical or procedural problems themselves almost always become the basis for specific, mandatory changes, be it a technical modification of a certain component or system of a particular type of aircraft, a revision of established flight restrictions or procedures, or a change in the training program for flight personnel, designed to prevent the recurrence of a similar tragedy in the future. Every detail has its own story. Every decision has its own price. And military aviation continues to develop, solving problems today, the answers to which tomorrow will become a new chapter of this endless story.